Alpha Centauri. The name itself whispers of adventure, of the next great frontier. It's our nearest stellar neighbor, a beacon in the cosmic dark. Yet, it remains forbiddingly far. Tonight, we explore why Next Door in Space is a journey that pushes against the very limits of human ingenuity, endurance, and imagination. Let's begin with the staggering, almost incomprehensible scale of the distance. Alpha Centauri is about 4.37 light-years away. A light-year is the distance light travels in a year, screaming through the void at 300,000 kilometers per second. That's nearly 10 trillion kilometers, multiplied by 4. To truly feel this scale, consider our own cosmic backyard. The distance from Earth to the Sun is 1 astronomical unit, or AU. Light crosses this gap in just over 8 minutes. Alpha Centauri is over 270,000 of these astronomical units away. It's not the next town over, it's a journey to another continent, on a world we haven't even discovered yet. So, how fast can we go? Our fastest emissaries, the Voyager and New Horizons probes, sprint through space at tens of kilometers per second. Yet even at these blistering speeds, a trip to Alpha Centauri would take them tens of thousands of years. The fundamental barrier is the tyranny of the rocket equation. To go faster, you need more fuel. But that fuel has mass, which means you need even more fuel to push the fuel you just added. It's a law of diminishing returns written in fire and steel. With chemical rockets, the kind that took us to the moon, most of your starship becomes nothing more than a giant fuel tank, leaving precious little room for a payload, let alone a crew. What about more efficient engines? Electric thrusters, like ion drives and Hall engines, are the marathon runners of space travel. They sip propellant with incredible efficiency, using powerful electric and magnetic fields to accelerate charged particles to high speeds. They can thrust continuously for months, even years. But their push is incredibly gentle, like the pressure of a piece of paper resting on your hand. They are perfect for slowly adjusting orbits or cruising through the solar system, but for an interstellar sprint, they lack the necessary brute force. To make them work, you'd need a power source so massive it would negate their efficiency advantage. To truly break free, we need to tap into the atom. Nuclear thermal rockets promise double the efficiency of chemical engines, using a fission reactor to superheat propellant. Project Orion, a concept from the atomic age, envisioned detonating a series of nuclear bombs behind the ship, riding the shockwaves to the stars. While powerful, these concepts still put the journey time in the centuries, and they come with immense engineering challenges and profound ethical questions about launching a trail of nuclear fallout through space. Further on the horizon lies fusion, the power source of the stars themselves. Concepts like Project Daedalus imagined a massive probe powered by igniting tiny pellets of deuterium and helium-3. But sustaining a controlled fusion reaction, surviving the intense heat and radiation, and sourcing the rare fuel are all monumental challenges we are nowhere near solving. And then there's antimatter, the ultimate fuel, converting mass to energy with 100% efficiency. But we can produce it only in microscopic quantities at astronomical cost, and we have no idea how to store it safely for more than a few minutes. For now, it remains the most powerful engine that exists only on paper. But what if the engine wasn't on the ship at all? This is the revolutionary idea behind beamed propulsion and projects like Breakthrough Starshot. Instead of carrying its fuel, the spacecraft is a tiny gram-scale star chip attached to an ultralight sail. From Earth, a colossal kilometer-wide phased array of lasers focuses a beam of immense power onto the sail, accelerating it to an incredible 20% of the speed of light. At that velocity, the journey to Alpha Centauri could be cut down to just over 20 years. It's a brilliant solution that bypasses the rocket equation entirely. But it creates its own problems. The probe is minuscule and fragile. How do you aim it, communicate with it across light years, and ensure it survives the journey? And most critically, how do you slow it down? The void between stars is not empty. At relativistic speeds, even a tiny grain of dust carries the kinetic energy of a bomb. A collision would instantly vaporize an unshielded probe. Shields can be designed, but every layer adds mass, and mass is the mortal enemy of speed. Then there's the radiation. The galaxy is awash in high-energy cosmic rays, atomic nuclei stripped of their electrons and accelerated to near-light speed by ancient supernovae. For a crewed mission, this constant bombardment would shred DNA and make long-term survival impossible without massive, heavy shielding. For a robotic probe, it threatens to fry sensitive electronics, turning our brilliant messenger into a dead piece of silicon. The challenges don't end with the journey. They intensify upon arrival. Navigation is an unforgiving science. You can't just aim for where Alpha Centauri is now. You must aim for where it will be decades or centuries in the future, accounting for the proper motion of every star. A tiny error in your initial trajectory, measured in microradians, could cause you to miss the system entirely. But the biggest question is deceleration. Getting there is only half the problem. How do you stop? You can't carry enough fuel to brake, and aerobraking in a star's atmosphere at a fraction of light speed is a fantasy. Concepts like magnetic sails, or magsails, propose using a powerful magnetic field to interact with the stellar wind, creating a slow, gentle drag. But this would add years, even decades, to the mission, and the technology is entirely theoretical. Without a solution for slowing down, our mission becomes a flyby, a fleeting glimpse before plunging back into the eternal dark. And what of the destination itself? Alpha Centauri is a triple star system. Alpha Centauri A and B are a pair of sun-like stars, orbiting each other closely. Farther out lies Proxima Centauri, a small, dim red dwarf. We know Proxima has at least one rocky planet, Proxima b, orbiting within its habitable zone. It's a tantalizing target, but Proxima is a flare star, prone to violent outbursts of radiation that could sterilize the surface of any nearby world. While tempting planets may exist around A and B as well, habitability is far from a guarantee. Our destination may be beautiful, but it could also be deadly. Even if our probe arrives safely, the conversation will be a slow one. The speed of light, our cosmic speed limit, also governs communication. A signal from Alpha Centauri would take over 4 years to reach us. A simple, "We've arrived" message would begin a nearly 9-year round trip for confirmation. Our tiny probe would need to shout its findings with a powerful transmitter, aimed perfectly at a home it can no longer see. And what of relativity? Doesn't time slow down at high speeds? Yes, but the effect is only significant as you approach the speed of light. For a probe at 20% of c, time dilation is modest. For every 20 years that pass on Earth, about 19.5 will have passed on the ship. Physics allows the journey. It's the engineering and the energy budgets that hold us back. Ultimately, the cost is the final towering barrier. The resources required are staggering. A laser array for beamed propulsion would be the largest structure ever built, requiring a power source rivaling that of a small country. The research and development, the decades of construction, the global coordination, this is not a mission for one nation or one company. Interstellar flight is a civilization-scale project demanding a unity of purpose and a commitment of resources that spans generations. It asks us to invest in a future we may not live to see. And yet, the dream endures. The pursuit of this seemingly impossible goal pays dividends today. The challenges of interstellar travel force us to develop better propulsion systems, more resilient spacecraft, and more precise navigation. We learn to build closed-loop life support systems for long-duration missions in our own solar system. We sharpen our maps of the cosmos, peering deeper into the dark. Every problem we solve, every small step we take, teaches us how to live and work farther from home. We will not leap to Alpha Centauri tomorrow, or even in the next century. The obstacles of distance, energy, and time are too immense. But the human spirit is relentless. With patience, with ingenuity, and with the courage to undertake journeys that will outlast us, we will continue to stitch a path through the dark. Not with a single giant leap, but one practical, determined step at a time. The stars will wait for us.